Okay, here we are with lesson 14, the decimal expansion of pi. You'll need for this lesson graph paper, compass, colored pencils, and a calculator. You might want to consider using the big half-inch graph paper that I have provided for you, or you can use regular style graph paper also. Alright, so for the opening exercise, go ahead and complete that, and then continue the video to check your answers. Alright, you should be done with the opening exercise, and so check your answers. If you have any questions, write them down and bring them to class. Alright, let's go ahead and discuss and also start with our activity. So the number pi is defined as the area of a unit circle. A unit circle is a circle with a radius of 1 unit. In the past, you may have thought that the number pi as a ratio of the circumference to the diameter of a circle. Our goal in this lesson is to determine the decimal expansion of pi. What do you think that is? You will likely state that the decimal expansion of pi is 3.14 because that is the number you have used in the past to approximate pi. The number 3.14 is often used to approximate pi, but it's not its decimal expansion. How might we determine its real decimal expansion? To determine the decimal expansion of pi, we will use the fact that the number pi is the area of a unit circle together with the counting strategy used in opening exercise Part C, subpart 1. Since the area of a unit circle is equal to pi, and we will use the counting squares, we can decrease our work by focusing on the area of just 1/4 of the circle. What is the area of 1/4 of a unit circle? Since the unit circle has an area of pi, then 1/4 pi will be the area of 1/4 of a unit circle. So on a piece of paper, or a piece of graph paper, mark a center O near the center of the paper. Use your ruler and draw 2 lines through O, one horizontal and one vertical. Our unit will be 10 of the grid squares on the graph paper. You're going to use your compass to measure 10 of the grid squares and then make an arc to represent the outer edge of the quarter circle. Make sure your arc intersects the horizontal and vertical lines you drew. So let's go ahead and demonstrate that. So here we have our unit, or our graph paper. I'm going to do this on several types of graph paper. And so if we've marked a center O, and this mark right here is 10 units away. Now we want to make sure that we have our grid lines. So we're going to go ahead and draw our horizontal line and our vertical line. Then using our compass, if this is 10 grids, we can count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then what we do is we make sure that our point and our pencil are lined up, and then go ahead and draw the half circle. Right, and then you might need to fill it in a little bit heavier, but in this particular case we have a 10 by 10 quarter circle. If you have smaller paper or smaller grids, then again it's the same thing. We want 10 lines, and we would make sure that The only problem with using smaller graph paper is the fact that it's going to be harder to count the squares and the pieces that we're looking for. But we can also go even smaller, and we'll talk about this later. But if we use even smaller graph paper, and based on that first circle, this ends up being 25 squares, 25 by 25. And this would give us an even more precise estimate of pi. So the smaller the squares are, the more precise we can get with our approximation of pi. But what we're going to do, and again, I've provided you with this size sheet of paper, or you can go back to the first one that we did. But if you want to do this, this is going to make it a lot easier to read. It's just kind of hard to draw the circle here. But make sure it is 10 grid lines again. Oops. And then go ahead and trace your circle. And you might have to fill it in so so you can see it a little bit better. But in essence, you should have a circle that starts at 10 and finishes at 10 at the top here. And so what we have, and you can thicken this up so you can see the lines, our vertical line here, or you can use colored pencils if you want to make it thicker, and our horizontal line. And then make sure you call this O, which is the center of our circle. So what we're trying to do is create a quarter circle so that we can continue our activity. So once you are done making your quarter circle, then go ahead and continue the video. All right, so you should have a quarter circle drawn. What we now have are inner squares, which are those that are inside the quarter circle, and outer squares, which are those that are outside the quarter circle. What we want to do is mark a border just inside the circle and just outside the circle, but as close to the arc of the circle as possible. We're going to mark a border inside the circle that captures all of the whole squares. You should not include any partial squares in this border, and this will be on the next slide. It will be shown in red. Mark a border just outside the arc that contains all of the whole squares within the quarter circle and parts of the squares that are just outside the circle, and that will be shown in black. So this is what we want to do. So again, this is the same. It should be a 10 by 10 if you count 10 and 10 up. So what you should have is the same thing. It doesn't matter what size your squares are, but you should be able to make a red line, and this is where your colored pencils come in handy, of 4 blocks, then drop down 1, then 2 blocks, then drop down 1, so on and so forth. When you do the outside, you're going to go over 5 blocks, then down 1, then over 1, then down 1. So whichever 2 colors you want to use, make sure you make your lines heavy and thick so that you can see them easily. So the squares of the grid paper are congruent. That is, they are all equal in size and thus area. So we're going to let R sub 2 denote the totality of all of the inner squares, and S sub 2 is the totality of all of the outer squares. Then clearly, if we do that, R sub 2 is going to be less or fewer squares than pi divided by 4. Remember, that's 1/4 pi. If pi is the area of the unit circle, then 1/4 pi is the area of this quarter circle. And instead of just calling it 1/4 pi, we're going to do pi divided by 4. And that's going to be less than S sub 2, which is all this black squares, or all the squares up until the black border. So count how many squares are contained within R sub 2 and S sub 2. So what we would do is we would count starting here. So here's the first square, second square, third square, fourth square. We're not going to go beyond, and then we would keep counting. So 5, and there you should end up with 69 inner squares. So if you count all of these, by the time you get down to the bottom here, you should be at 69. Then you're going to go ahead and count all the squares. So if there's 69, then starting and counting the squares that we missed up into the black border, then this first square would be square number 70. And we would count the next square, 71, 72, 73, 74, 75, 76, and so on. So now you would keep continually, or you would count some more. You'd count these squares, and down here. And when you get done, you should be at 86. So 69 inner squares and 86 outer squares. So if we consider the area of a square with side length equal to 10 squares of the grid paper, then R sub 2 is equal to 69 out of 100 squares. What does S sub 2 equal? Well, you should have said the area of S sub 2 is 86 out of 100 squares. So by substitution, we see that R sub 2 is less than pi divided by 4 is less than S sub 2. Then 69 hundredths is less than pi sub 4, and that should be less than 86 hundredths. So now we have 69 hundredths is less than pi divided by 4, and that is less than 86 hundredths. So now we're going to multiply by 4. We want to get rid of our fraction and turn it into, in this instance, just pi. And so when we do that, we get 2.76 is less than pi, which is less than 3.44. Is this inequality showing a value for pi that we know to be accurate? Well, yes, because since we frequently use 3 and 14 hundredths to represent pi, this would make sense and be a true statement. 2.76 is less than 3.14, which is less than 3.44. So of course we can improve our estimate of pi by taking another look at those grid squares. We're going to label the columns A through H at the top like below. So go ahead and pause the video and label your columns just as it is in the square. All right, after labeling the columns, we're going to look at the top row, highlighted here in yellow. So columns A through B. There are some significant portions of squares that were not included in the area of the quarter circle. If we wanted to represent that portion of the circle with a whole number of grid squares, about how many do you think that would be? So looking at all 4 of these, if we counted, we just want the partial parts now, how many squares do you think we could get here? Well, it looks like there would be at least 2. We could make 2 full squares, but less than 3. So if we took the little pieces and parts here, we could probably make 2 full squares, but not 3. So we're looking at these little bitty pieces. Now we're going to take a look at the next column, C and D, which I've highlighted in yellow. Using the similar reasoning about how many grid squares do you think we should add to the area of the quarter circle using just columns C and D. So if you look at, we have this little piece, and this piece, and this piece. Well, it looks like we could add maybe 1 more square to the quarter circle. So more than 1, but less than 2. But right now we're going to go with 1. Now we're moving to E and F. If we look at that, how many do you think we would have? Well, again, because we're looking at this quarter, or it almost looks like it's cut in half, so this 1/2 plus this other half would be another 1 square. Then we go back to column G. If we look at the pieces for column G, we have this little piece here and this piece. Then again, it looks like we would add about 1 more square to our area. And last but not least, since this side, column H, is about the same as column AB, since it looks the same, we're going to add 2 more to the area. So we began by counting only the number of whole squares within the border of the quarter circle, and that was 69. Now, by estimating partial amounts of the squares in columns A through H, we have decided to improve our estimate by adding another 2 plus 1 plus 1 plus 1 and another 2 squares, making our total number of grid squares represented by the quarter circle as 76. Therefore, we have refined R sub 2 to be 76, which means that 76 hundredths is less than pi divided by 4, which is less than 86 over 100. And this is equal to 304 over 100 is less than pi, which is less than 344 over 100. Remember, the way we did that was multiply everything by 4. So now we have 3 400ths is less than pi, which is less than 3 44 hundredths. So does this inequality still represent a value we expect pi to be? Well, yes, because 3 4 hundredths is less than 3 14 hundredths, which is less than 3 44 hundredths. So we can reason the same way as we did before to refine the estimate of S sub 2. So I'll refine the estimate of S sub 2 using the same method. Continue the video to check your answer. Alright, so you should have added up the partial squares, and you might have come up with something close, but we're going to go ahead and use 80 instead of the original 86. So if you ended up with 81 or 79 or somewhere along those lines, we're going to just go ahead and use 80. So now we have 76 over 100 is less than pi divided by 4 is less than 80 divided by 100. When we multiply by 4 throughout, we get 3 4 hundredths is less than pi is less than 3 2 tenths, or 20 hundredths. So does this inequality still represent a value we expect pi to be? Well, yes, because 3 4 hundredths is less than 3 14 hundredths, which is less than 3 20 hundredths. So these are certainly respectable approximations of pi. What would make our approximation better? We could decrease the size of the squares we are using to develop the area of the quarter circle. We could go back and make better estimations of the squares to include in R sub 2 and the squares not to include in S sub 2. So suppose we divide each square horizontally and vertically so that instead of 100 squares, we now have 400 squares. Then the inner region, R sub 2, is composed of 294 squares, and the outer region, S sub 2, is composed of 333 squares. This means that 294 over 400 is less than pi divided by 4, which is less than 333 over 400. Multiplying by 4 throughout, we have 294 over 100 is less than pi, which is less than 333 over 100. And 2 94 hundredths is less than pi, which is less than 3 33 hundredths. Then by looking at the partial squares that can be combined, the refined estimate of R sub 2 is 310 and S sub 2 is 321. Then the inequality is 310 over 400 is less than pi divided by 4 is less than 321 over 400. And then multiplying by 4 throughout, we have 310 over 100 is less than pi, which is less than 321 over 100. So 3 and 1/10 is less than pi, which is less than 3 and 21/100ths. And how does this inequality compare to what we know pi to be? Well, this inequality is quite accurate, as 3 and 10/100ths is less than 3 and 14/100ths, which is less than 3 and 21/100ths. There is only a difference of 4/100ths for the lower region and 7/100ths for the upper region. So we could continue the process of refining our estimate several more times to see that 3.14159 is less than pi, which is less than 3.14160, and then continue on to get an even more precise estimate of pi. But at this point, it should be clear that we have a fairly good one already. We finished by making one more observation about pi and irrational numbers in general. When we take the square of an irrational number such as pi, we are doing it formally without exactly knowing what the value of pi squared. Since we can use a calculator to show that 3.14159 is less than pi, which is less than 3.14160, then we also know that 3.14159 squared is less than pi squared, which is less than 3.14160 squared. And this would give you 9.86958777281, which is less than pi squared, which is less than 9.86965056. Notice that the first four digits, 9.869, appear in the inequality. Therefore, we can say that pi squared is 9.869 and is correct up to 3 decimal digits. Alright, so now it's time for you to do exercises 1 through 4. Complete these exercises using a calculator. The answers given were created by an online calculator. If you are using a handheld, your answers will be truncated to 8 spaces. However, this will not affect the estimate of the irrational numbers. So go ahead and do exercises 1 through 4, and then continue the video to check your answers. Alright, you should be done with the exercises. Go ahead and compare your answers to what is here, and if you have any questions, make a note and bring them to class. Alright, let's wrap this up. The area of a unit circle is pi. We learned a method to estimate the value of pi using graph paper, a unit circle, and areas. When we square the decimal expansion of an irrational number, we are doing it formally. This is similar to using approximation for computations. For that reason, we may only be accurate to a few decimal digits. All right, we'll see you in class.